All right, this is Mr. Hendrickson here. I'm going to give you the quick synopsis of practice file 6.1. So number one here, how much work is needed to lift an object that weighs 200 newtons to a height of 4 meters? Work is force times displacement. So we know that the work applied is the force applied is 200 newtons, and the displacement is going to be 4 meters here. So our work is 800 joules for number one. Okay, power, remember, is the amount of work we're doing per unit time or work per second. So power is work over time. So we're lifting that 200 Newton object to 4 meters. So we know the work is 800 joules. So all we need to do is sub that in along with our time. So power will be 800 joules of work done in 4 seconds. So our power should be 200 watts, which is the unit for power. Okay, check your work there. Number three, what is the power output of an engine that does 60,000 joules in 10 seconds? Again, power is work over time. We're given the work is 60,000 joules, and we're given the time is 10 seconds. 60,000 divided by 10 will give us a power of 6,000 watts. Again, that just means 6,000 joules of energy are converted per second. 6,000 joules per second. All right, number four. So you've got your ramp problem here. So we're supposed to figure out what the advantage is of this incline. So we have a block of ice weighing 500 newtons. So we already know, right, the weight or the force that's going to be required to lift the block. So what we're going to do is we're going to figure out how much work is required to go straight up from the floor to the top of the ramp using the shortest path there, which is 3 meters. So work will be force times displacement. So the work is going to be our 500 newtons times the displacement of 3 meters. So the work to go straight up is going to be 1,500 joules. That's significant because that also means, folks, that the work to get up the ramp will also be 1,500 joules. Okay, remember the ramp is longer, so it's going to require less force. So we know the work to go up the ramp is 1,500 joules. The force applied up the ramp we don't know, and the displacement is going to be 6 meters. So we can go ahead and take our 1,500 joules and divide 6 meters into that value there, and I believe we will get 250 newtons is the force applied to go up the ramp. Okay, so then the question is, what is the mechanical advantage to go up the ramp? So mechanical advantage, okay, is going to be our applied force divided by the ramp force, okay? So the mechanical advantage here is going to be to go straight up requires 500 newtons of force. To go up the ramp only requires 250 newtons of force. That means our mechanical advantage here is going to be 2. Again, essentially that just means that it's 2 times easier to go up the ramp than it would be to go straight up. Okay, another quick way that you can find this is by simply comparing the lengths of the ramp. Okay, remember, with ramps, we trade force for displacement. So if I decide to go up a ramp that is twice as long, it's going to be twice as easy, which is what we see here, right? Using the ramp is 250 newtons, going straight up is 500. It's twice as easy. Okay, so how much force is, again, required to get up the ramp? We just did that one. That, of course, is 250 newtons as well. So make sure you've got all the work there for that ramp problem. All right, so now we've got 3 different ramps. Or 3 different scenarios, rather, and 2 different ramps. Okay, so we've got a block that starts 5 meters above the ground, and we've got option 1 where we simply drop the block straight down. We got option 2 where the block goes down the straight ramp. we got option 3 where the block goes down the curved ramp. In all 3 scenarios, they want us to determine how fast is the block going when it reaches the bottom. The key with this, folks, is that our block is always starting with the same amount of potential and always getting down to the ground level. That means that all 3 cases, the block should have the exact same kinetic energy and the exact same velocity. So here's what we're going to use to answer this. We know that the block has potential energy at the top and kinetic energy at the bottom only. Okay, we know that the potential energy at the beginning, the initial potential, will be equal to the kinetic energy at the end. Okay, so how do we find potential energy? Well, we know that's mgh, mass times gravity times the initial height. And we know kinetic energy is 1/2 mvf squared, 1/2 mass times final velocity squared. What you'll notice here, and we've seen this before, is that mass shows up on both sides of the equation. That's important because that means that we can strike mass out here. Okay, we can factor it out. We don't need it to solve this problem. And that's important because you'll notice from the prompt here that we do not have mass. We do not know that information. So it's good that we don't need it because we don't have it. So what we're going to need to do here is rearrange this equation to solve for velocity. So I want to solve for my VF squared. So I'm going to multiply both sides by 2. I'm going to get 2GHI. Okay, and then I'm going to go ahead and root that to solve for final velocity. So I'm going to do 2GH and root it, and that will give me my velocity here. So I'm going to go 2 times gravity, 10 meters per second squared, times my height, which is 5 meters. And that's going to give me my final velocity. 2 times 10, of course, is 20. 5 times 20 is 100. We're going to go root 100 to find our final velocity. And that, of course, folks, is just 10 meters per second squared. Okay, now, as it turns out, all 3 blocks start 5 meters above the ground, okay? All 3 blocks end up at the ground. So in all of these scenarios, our blocks are starting with the same potential energy, ending with the same kinetic energy. So our solution here for case 1 applies to both cases 2 and 3. So as it turns out, folks, the work is going to be completely the same, identical, okay? Because in all scenarios here, of course, our block is starting at the same height and ending at the exact same height. So the solutions for all 3 will be the same. And again, we don't care about the path the block takes. All we care about is where does the block start and where does the block end, and that will determine our change in energy. All right. Next part here with block A and B, they want us to just simply determine which block gets to the bottom first. That is going to be A. Okay, it's going to have a greater acceleration because it is more vertical. Okay, it's going to reach a peak speed, top speed, much earlier than B. Okay, it's a greater acceleration, and it's also a shorter path. Okay. Now, you should not be confused because A and B both end at the same position and start at the same position. So both A and B will end with the same velocity, but block A will get to the bottom first because the path is shorter. It accelerates at a higher rate and reaches peak speed earlier. Okay. Kinetic and potential energy of a block freely sliding down this ramp are shown. We're going to find the missing values. Okay, again, all we need to know here, guys, is that our total energy is equal to our potential plus our kinetic. Okay, what we know is that at the end, the total energy is 75 joules. So any combination that we do here, we know that the sum of our potential plus our kinetic must be 75 joules. So we just have to ask ourselves, what does our missing term need to be so that our total energy will be 75? So 0 plus 75 joules is 75. 50 plus 25 joules is 75, and 25 joules plus 50 is 75. What you should notice here is that at the very top, it's all potential, no kinetic. As we begin to fall, where our position is getting lower, so the potential decreases, the kinetic increases because the block is going faster the lower it falls. Okay, until the block's almost at the bottom, the potential is pretty low there, only 25 joules, and the block's moving at a very high rate, so the kinetic is 50. Until we get to the very bottom here, and we have no potential and all kinetic. Okay, and then lastly here, we've got our bead on a track here. So we've got our bead starting 5 meters above this position. The bead is going to fall down here, keep going down, come back up, and then fall down again. They want us to find the speed of the bead at various positions. You'll notice here, folks, that we do not have mass. Okay, the solution here is going to look a lot like what we did on a previous problem where we said that our bead has all potential here and then kinetic, all kinetic at B, D, and E. What we can then say is the potential at the top, right? Our initial potential is going to be equal to our kinetic at the end. If that's the case, we know MGHI is going to be equal to 1/2 MVF squared. Our masses will fall out, and then we rearrange the equation, and we end up with this one, which should look awfully familiar. Root 2GH equals VF. Okay, so all we need to do here, folks, is plug in our 5 for our height and 10 for gravity, which is actually the exact same numbers that we had on the previous ramp problem. So we're going to have the root of 2 times 10 times 5 meters high equals VF. If you crunch the numbers on that, you should get 10 meters per second is the final velocity. So when our bead falls, right, from the top to this position here, okay, it goes from all potential to all kinetic. Again, we're defining this as our 0 position. We can define it however we want. Okay, so I'm defining this as my 0 position, so the potential here is going to be equal to the kinetic here. So that means that at point B, my velocity is 10 meters per second. Now, the ball is going to fall lower, but then it comes back up. So it speeds up as it falls, but then slows down as it comes back up and reaches the exact same height again. So at point D, we're going to find that, again, the velocity is 10 meters per second. Okay, after point D, the ball goes up, slows down, but then falls back down again and speeds up till it reaches point E. Point E is the same height again. Point E will have the same velocity. Now, there is one point on here where the velocity is greater than 10, and that is point C, where the ball has fallen a little bit further. Okay, so if that ball goes even lower, right, there is more conversion of potential to kinetic, and that ball is now even traveling faster than 10 meters per second. We don't know what it is because we don't know how far it's fallen, but we do know that C must be faster than those 3 points. Okay, and then lastly, they want us to determine what would happen, okay, to the wind behind a windmill. Okay, so in other words, right, wind is going into these windmills, okay, and let's say there's a person standing back here, right? What would happen if we completely eliminated all of these windmills, if these were gone? What would happen to the wind that the person behind would feel? Well, remember, what's happening is the wind is coming in and has kinetic energy. That kinetic energy is striking these fans, and that kinetic energy is being converted into mechanical energy, or if it's a turbine, electrical energy. Okay, so the energy of the wind, right, is decreasing, and the energy of the fans is increasing. So our wind is losing kinetic energy when it hits the fan. So basically what's happening here, right, is our wind is losing motion when it encounters the fan. So if we remove the fans, our wind will continue to have kinetic energy. It will continue to have its motion. So if we remove these fans, the wind will be windier or more windy behind the fans because the air particles of the wind will have more kinetic energy. Or in other words, motion. Okay, there you go. So go through, double check your file here. You should already have all the right answers via the formative, but now you have your explanations. So go ahead, make sure these are all done, and we will see you on Monday. Have a great weekend.